Hello, my name is Bob D. Hilster and I am your particle model guru. Today we're talking about cold fusion. This series of topics have been all related, starting with a universal solvent, water, trying to explain something about the electrolyte, then the wet cell battery, did electrolysis the last time, and this time it's about cold fusion, and you'll see that's very much like electrolysis. One of the interesting aspects of what is not just proposed but claimed in cold fusion is that there is excess heat during the electrolysis process. So here's a drawing from the link of a setup for cold fusion, and yes, you'll see it's very, very much like the electrolysis. What you have is a normal battery feeding a current into a cathode. You have an anode and a return. There's a Dewar flask here in the center containing an electrolyte made of heavy water and an electrolyte, although I didn't get a clear understanding of what that was. And this flask is sitting in a water bath, presumably to help keep the process of this heat cool down. And heavy water is what's being used here, which is heavy water is deuterium. Deuterium has two protons instead of one proton, like hydrogen has one, deuterium has two, tritium has three, and heavy water is D20 instead of H2O. And what they're claiming is that the electrical energy in, at some point in time, the electrical energy in was less than the amount of heat energy out. The electrical energy in was less than the heat energy out. That's what's claimed. And so let's take a look at what we can understand about this. So from Wikipedia, this is what they say about cold fusion. It's a hypothesized type of nuclear reaction that would occur at room temperature. This is compared to the hot fusion, which takes place naturally within stars and under immense pressure and at temperatures of 1,000,000 degrees, and so it's hot fusion, not cold fusion. Apparently there's another type of fusion where they use muons to combine with other elements and fuse together. However, there is no currently accepted theoretical model that would allow this to occur. No model, but they claim that they do get it. Now, this is a little bit more about fusion, and they're talking about a fusion process that produces a nucleus lighter than iron 56 or nickel 62. And will generally yield a net energy release, the increase of heat. And they talk about mass and binding energy per nucleon and all of that detail. But in the end, depending on whether there is a mass increase or a mass decrease, you end up with either an exothermic process, that is releasing heat, or an endothermic process, which is absorbing heat. And so what they're trying to do in cold fusion is the releasing of heat by combining elements. Now, one of the things I don't find very often is the chemical equation in this electrochemical process or electronuclear process. There are some diagrams showing pictures, but not very clear. Well, there was a news release back 9 years ago where Scott Pelley was interviewing somebody, and part of this Interview was talking about that in 1989, Fleischmann and Pons, who were the first ones to have done this, claimed they got this excess heat during a cold fusion process. They called it cold fusion, but obviously it's confusing today as to whether that is truly what's happening. And so scientists today call it a nuclear effect rather than cold fusion. At least 20 labs working independently, and this was in 2009, have published reports of excess heat up to 25 times greater than the electrical energy going in. Wow, that's a lot. They were interviewing a man named Michael McKubre. I hope I say that right. He's been working on this science since it was first discredited, and it made the headlines when Pons and Fleischmann did that. Scott Pelley was interviewing Michael, and Scott asked the question, to work on this issue is almost to put your scientific credibility at risk. I wonder why you've done it. And his answer was, my belief is that if there is just 1% chance that Fleischmann and Pons were correct, I now believe that and he now believes the possibility is actually 99%. He has a duty to work on it. It's a good point. We, as scientists, if there is something happening that we can't explain, that's the scientist's job. But some scientists say that this is just an anomaly and it's hard to make happen, and so I'll just ignore it. Well, number one, there are no anomalies in nature. Nature doesn't do that. Nature does what nature does, and if it happened, it happened. Now, what really goes on is that what we expect to happen and what we measure doesn't agree. It's called a discrepancy. It's up to the scientists to figure out what that discrepancy is, if they can find it. But just to excuse it as an anomaly and walk away, that's not science. That's not science at all. Some are saying that it did happen and it's worth the effort to get it right, which we just read from Scott Pelley's interview. But they're looking at it as if they're getting some free energy, and somehow that just doesn't set right with me. To me, there is no such thing as free energy. Once it's explained and understood, maybe we'll understand what's going on. But let's see what happens. So what is claimed, at some point in the electrolysis process, there is more energy, heat energy, generated than the amount of electrical energy used. Cold fusion is suggested, but there's no model. So let's just apply the particle model, see what could be done to gain excess heat and where it could come from. All right, heat, as I've discussed before, is caused by atoms that vibrate at a higher rate, gives us higher heat. Atoms that are not vibrating at all, it doesn't have heat. We can't measure any thermal energy that way. To get more heat energy out than the electrical energy you put in does not make sense unless there's more happening that is not normally understood. So let's take a look at this simple diagram again, and now I've added my particle model ideas where out of the battery, G1 particles flowing into the cathode. By the way, I believe these are palladium. And typically I would say that a lot of them are going this way to make a complete electrical circuit. But the fact is, as the G1 particles move through this cathode, a lot of them may just pass straight through, but a lot of them scatter and move off in all directions. It's much like an antenna. When I talked about an antenna, and a FM transmitter sends G1 particles to an antenna, they scatter off of the antenna and move out in all directions. So what I'm drawing here is not only the flow this way, but I'm drawing the flow, some of it going this way, but there's no anode over there. They just move out. What I'm trying to suggest is that you have G1 particles moving outward from the in a plane. They're moving both left and right, forward and back, out from the cathode outward. This is supposed to be an outward motion. This is outward. This is supposed to be outward, and that is. But there's also the G2 force field all the way around the flask, and you can try to analyze the strength of these. But generally the strength of this net force field here and here is about the same, and it gets less and less until it gets here. Same thing on this side, and it's basically reasonably balanced so that when the G2 forces reach here, they're equal and opposite. But what you have here is a possibility that the G2 gravity this way and the G1 gravity this way, or G1 flow this way, are working against each other, pushing the heavy water back and forth. We have two opposing forces, G1 gravity and G2 gravity, are causing the atoms and molecules in the electrolyte to move in opposite direction. This is one possibility. I'm not saying this is really what happens. I don't know. But this process could cause heavy water and the electrolyte to vibrate at a higher rate. And when it vibrates at a higher rate, it gets measured as higher heat. So the extra energy resulting in the excess heat could be coming from the G2 gravity. So I could change the equation from the electrical energy in plus the G2 energy giving the heat energy. In this sense, it's not free, because the equation balances, theoretically balances. Now let me talk a little bit about something I haven't mentioned, and this is called what I call an instant of time. And I'm going to go into my actual definition of time, which I also have not mentioned. Time, to me, is a man-made idea for measuring motion. Nature doesn't know what time it is, or what time itself is. And in fact, time only moves forward because we humans set the value of time only in an increasing sense. So we set a time in the past, some point in time in the past, that's 0 seconds, and we come all the way up to now, and we have gazillion seconds pass. The next event to happen, when we assign the time stamp for that, it's always increasing. It's we humans that define time. It's a concept. It moves forward because the value is always increasing. The next event, we never mark the next event with a timestamp that is smaller than our current time. That's why time always moves forward. People talk about time going backwards. No, we don't use it that way. But time is also a scalar, and this is where the instant of time comes. I can make time very, very large or very small. I can make time be a day, a month, a year, a decade, a century, and more. But I can also make time very small. I can make it a microsecond, a femtosecond, and even smaller. Make it as small as I want because it's a scalar. It's my own invention, and mathematically I can take it down and assume that I got this tiny instant of time in which I can observe what's going on. So what does this tell me? It says for a given system, I can make time small enough, and now I'm talking about cold fusion or electrolysis. I can make time small enough that only one particle interacts with an object during an instant of time. And so what you end up having is you got the G2 gravity pushing on a particle this way, and then sometime later the G1 gravity pushes the other way. And these are happening in instants of time, which is why you don't see compression when you do this. If they were all happening at exactly the same time, you'd get compression rather than oscillation. So that's why you can have forces pushing on you, gravity forces pushing on you, and I don't feel the compression. I feel atmospheric compression, but I don't feel gravity compression. Anyway, one other way that you might consider using is to use pulsating DC. The idea of pulsating DC is that you get these pulses going, periodic pulses at some rate that matches with the maybe the natural frequency of the electrolyte, or in this case, if the repeating pulse could make the electrolyte move towards the side and then let it come back, then pulse it again, it would start to oscillate. How fast that would go, or you could make it go, I don't know, but by reducing the input power could give the apparent notion of an increased, an excess heat. Free energy. Well, no, I've already said free energy doesn't make sense. Scientists would like to have more energy out for less energy in. But if we get G2 gravity for free, because we're not generating that, then maybe we have a cheap source of energy. Just raising the possibility. The particle model here doesn't give a clear answer. It can only suggest that there are features of the particle model that may give clues, and these clues may help redirect the effort to get cold fusion to work, or whatever it is. Clearly, I haven't described it as a fusing process. There's not enough information for me to explain how that would work, and so it's not included in this presentation. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.